So when we dissolve a non-volatile solute in a solvent to form a solution, the vapor pressure of that new solution will be lower than the vapor pressure of the original solvent just by itself. So this is described by Raoult's law, which says that the vapor pressure of the new solution is equal to the mole fraction of the solvent multiplied by the original vapor pressure of the pure solvent. So let's look at an example. We have sodium sulfate being dissolved in water. And so the first thing we want to do is calculate the moles of each substance, the water and the sodium sulfate. So we get that there's 9.71 moles of water and 0.246 moles of sodium sulfate. So before we can carry on with the Raoult's law, we have to recognize that when we put sodium sulfate in the solution, since this is a soluble substance, it will dissolve into ions, according to this equation. So for every mole of sodium sulfate that we dissolve in the solution, 2 moles of sodium ions and 1 mole of sulfate ion will be produced. So if we put 1 mole in, we get a total of 3 moles out. There will be 3 moles of particles in the solution. So the total moles of solute is going to be 3 times this amount of solute that we put into the solution. So we get the total moles of solute will be 0.738 moles. So now we can calculate the mole fraction of the solvent, water. So we have the moles of water over the total moles, which is the moles of water plus the moles of all these ions. And so we get the mole fraction. And now we can just plug it into Raoult's law. So we have the mole fraction of water times the original vapor pressure of the pure water, which we get in the problem. So the new vapor pressure of this solution is 22.1 torr, which, as we expect, is less than the original pressure of the water. And so any solution that obeys Raoult's law is called an ideal solution, similar to how an ideal gas obeys the ideal gas law. So solutions have what's called colligative properties. And colligative properties only depend on the number of particles of solute there are. It doesn't depend what type of solute, only how many particles. So the 2 colligative properties we're going to be looking at are boiling point elevation and freezing point depression. So the definition of a boiling point of a liquid is when the vapor pressure of the liquid state is equal to the atmospheric pressure. So we just found out that a solute decreases the vapor pressure of the pure solvent. And so when we add a solute, then the solution will have a lower vapor pressure, which means we need to add, the temperature needs to be greater in order to get the vapor pressure to be higher, equal to the atmospheric pressure, which is the boiling point. So the boiling point of a solution will be higher than the boiling point of the pure solvent. And to calculate how much higher the boiling point will be, we use this equation. The change in the boiling point is equal to K, which is a constant specific to a solvent. Now you'll get that in the problem, times the molality of the solute, which, remember, is the moles of the solute divided by the kilograms of solvent. And similarly, when we have a solute in a solution, the decrease in the vapor pressure will cause the freezing point to decrease as well. Because remember, the definition of a freezing point is when the liquid state and the solid state have the same vapor pressure. So when we add the solute, the liquid will have a lower vapor pressure than the solid phase. So we need to decrease the temperature even further than normal until the solid phase has the same vapor pressure as the liquid phase. So the formula for freezing point depression is the same as boiling point elevation. How much the freezing point is lower is equal to a constant K times the molality of the solute. So for any solvent, it'll have two constants associated with it. One is for the boiling point equation, and one is for the freezing point equation. And so these equations are only for, solutes that don't split up into multiple particles. Remember, like in the last example, that sodium sulfate split into 3 ions when dissolved in solution. So when we have a case like that, we have to modify this equation. So we do that by just adding in what's called the Van Hoff factor into the equations. So the Van Hoff factor, this I, is the moles of particles in the solution divided by the moles of solute that were originally dissolved. So for example, for potassium sulfate, this will dissolve into 2 K plus ions and 1 sulfate ion. So for every mole of sodium or potassium sulfate that we dissolve, 3 moles of ions will be produced. So the Van Hoff factor is expected to be 3. So sometimes the actual value of the Van Hoff factor is less than the expected value that we get just from looking at how many ions will be produced when this dissolves. And this is due to ion pairing, which is basically at any moment in time, some of the ions in the solution will be clumped up together and therefore count as one effective particle.